Yeah, thanks very much. So I am the one who has to actually wake you up again after your lunch coma, I think. So change of gear a little bit. We go into epitaxy now. I think we learned a lot about defects and how materials grow in bulk, and a lot about the requirements for silicon carbide transistors and YESvGaN transistors. Let me just quickly introduce myself. My name is Bernd Schineller. I'm the Program Manager for Corporate Research and Innovation at AIXTRON, which is a company that specializes in CVD and MOCVD growth technology. And one of the things that is very important when you talk about, let's say, making electronic devices viable, are actually three things you need to consider. One is cost, the second is cost. If you still have time, you work on cost, because that's important. Okay, so a little outline of my talk. I'll just quickly introduce the company, and I will talk about the metallo-organic vapor phase epitaxy basics, because some of you may not know this technology. I know there's MO in there. Silicon carbide obviously is made by CVD, but the process is quite similar in the end. Then I talk about MOCVD tool design considerations for mass production. This is where cost comes in. Tuning capability and automation and defect avoidance. And I will talk about a couple of GaN-based device applications and growth results. Two examples here. Gallium nitride silicon on silicon heteroepitaxy for horizontal power transistors, and Farid touched on this a little bit, I think, gallium nitride and gallium nitride polyepitaxy for vertical power transistors. That's something that we're also involved in, although this is at a very, very early stage. And then I will talk about silicon carbide growth considerations and results in the same context. I must say, to my shame, I'm not the super special silicon carbide expert, so forgive me a little bit on that. So, who are we? We're a company that was founded near Aachen in Germany. We have a worldwide presence in 7 countries. It's a little bit outdated. We're now a little over 1,000 employees. And we were founded in 1983, that's about 40 years ago, so we're not really new anymore. We may not be as old as Bosch, for instance, but we're getting there. We never catch up, though. We are a publicly listed company since 1997, so we are a stock-listed company. So where are we? We're at the very border to the Netherlands and Belgium, and it took about 1 hour and 59 minutes to get here by train, which actually worked out, which is a big surprise sometimes. So this is where we are. And by the way, I let this out at the very beginning by hiring as well, so if you are interested in working for a progressive company, then just cross the line. So yeah, this is where we are, headquartered in Herzogenrath, which is 10 minutes north of Aachen, and we are in Cambridge as well, Santa Clara in the US, and main business is in Asia at this time, although we're seeing a lot of it come back to Europe at this time. So there's definitely being a shift in that outsourcing to Asia that we see. We provide deposition equipment to the compound, especially compound semiconductor display industry, mostly for optoelectronics and power electronics applications. Metal-organic chemical vapor deposition is the main part of our business, but we're also in plasma-enhanced chemical vapor deposition, PECVD, for instance, for carbon nanotubes, 2D materials, graphene. If anybody finds out what graphene is good for, let me know. But it's definitely something that we're in. And we would basically say it's actually 2 big businesses. One is power management, the other is LED and optoelectronics. Optoelectronics, lasers, VCSELs, very important. We have 100% market share on the iPhone. So if you have these face recognition features on your iPhone, that's 100% done. Our machines, as well as currently 100% on datacom lasers, which is big backbones, fiber communication. So 100% of these are made on our machines. And something that's very interesting I can't talk about today. Last year in Brixton, I don't know, I was able to talk a little bit about micro-LEDs, because this is a very interesting new field. But today I'll actually focus more on gallium nitride power electronics and silicon carbide. So, This is also interesting, maybe for some people who are not in the, let's say, equipment field. This is a revenue overview of the past 20 years. It starts in 1999, and you can see that there's quite a big change sometimes in the amount of machines and amount of revenue such a company makes. And the interesting part of this is that there have always been drivers that came along, like telecom, datacom, mobile phones, notebook backlighting, LED TV. This was very big, by the way. This was the world financial crisis. It's actually been some of our juiciest years. And then it dropped off again. And nowadays we're talking about lasers, power electronics, as well as micro LED displays. And this is very interesting for us because actually this is a revenue forecast. I think we're going to crack the $500 million revenue this year. And it's also a very diversified thing. Back in the past, it's always mostly been LEDs for lighting, and this has changed. And this is the picture that actually is a motivation for you guys to talk, to listen to me, because you might be asking, okay, why is he talking to us? And the reason is that I think we definitely have the market, the lion's share of the market. This is the total market of MOCVD systems. The source is Gartner here, and in 2021 was the record year. Three quarters of all MOCVD systems shipped worldwide came from our factory. It's been down a little bit to 70% this last year, but I think we're still big in the game. Okay, I'll skip that, and I go into the motivation for wide bandgap semiconductors. I think this is a bit of a repeat to some of the things that we've heard before, because I think everybody's hammering the same nail today. This is the picture that shows the motivation, operating frequency, and output power. This is logarithmic in both cases, and we can see the dominant silicon. The silicon is still dominant today. But we have those two nice semiconductors, gallium nitride and silicon carbide, coming up, and both of them are actually complementary in their applications. In the sense that for the gallium nitride, we're aiming more for the higher operating frequencies, whereas in the silicon carbide, we more go for, let's say, the higher output powers. So they don't really hurt each other, although, as we will see in the vertical gallium nitride transistors, we're trying to sort of expand the application of gallium nitride a little bit into the silicon carbide field, or at least we're trying to expand the bubble of gallium nitride a bit upwards into the more higher output powers. But that's for later. So I think all of us have seen this picture many times, and there's not much more to say about it. This is the food chain, if you will, for wide bandgap semiconductors. We start with the semiconductor capability. Most of you know we have high electron mobility, we have high thermal conductivity, and this then filters through the effective physical properties, the power electronics characteristics, all the way to the product benefit. And interesting, maybe I just pick out two things here. First is faster switching, reduced passive components, which leads to reduced cost. It's not just important that the transistor becomes less expensive. You can alleviate some of maybe higher cost by actually reducing the parasitic, or let's say, peripheral components such as inductances and capacitances in the circuit. Because usually the higher the switching frequency, the smaller those become. So you're actually ending up with a smaller, more compact device, or more compact circuit. And at the same time, the amount of raw materials that you put in, and this goes into the question of green tech and all these things, becomes a bit more fortunate when you can put a higher switching frequency. So that can reduce the cost just as well as maybe reduce the amount of, let's say, materials that put into these circuits. And the second, obviously, is reduced cooling components, and depending on the type of circuit, type of application that you have, you may need active cooling, and this is also not really a very good idea. So if you can go with passive cooling and so forth, then this is definitely also beneficial. And there's lots of other things like reduced energy consumption of such circuits and so forth. So this is from the International Energy Agency, and they've done a report. This is the Power Electronics Conversion Technology Annex PECTA from 2020, and they did a calculation. This is a bit of a potential calculation for wide bandgap semiconductors, in the sense that when you replace every power supply in these respective fields by a wide bandgap semiconductor. So essentially, you kick out all the machinery and all the stuff you have today, you replace it by wide bandgap 100%. You actually save 95 terawatt hours per year. And I think this number will be growing in the future as well. So this actually shows you the potential. And I've got this from our marketing. On a 6-inch wafer, you typically would get 5 to 6 battery electric vehicles out of a 6-inch wafer for the inverter for that car. So that also shows the potential amount of wafers that may be required in that field. Okay, I skip this page and I go to this one. This is just as an illustration. It's a bit older, but I think the general idea still holds. This is a comparison between silicon IGBT and a silicon carbide power transistor, and interesting here is over the percentage of load. So when we have the spec load at 100%, and this is the efficiency, by the way, the IGBT doesn't really perform that bad, so it comes quite close to the performance of the silicon carbide. This may be okay in the case that you are driving always, let's say, pedal to the metal. So this is the design point, if you will, for the circuit. But this is not how to operate, especially variable power supplies. So variable power supply may also be ending up maybe more than 20% drive range. And this is where actually you will see a lot more losses in case of the IGBT compared to the silicon carbide in this case. Another example, when we go to the switching frequency from, let's say, 20 to it's 120 or no, it's 100 kilohertz, and we compare the different technologies. This is the total power loss for comparable transistors. Again, silicon transistor, silicon carbide JFET, and the gallium nitride FET. We see that the silicon carbide, especially the gallium nitride, this is why this is earmarked for high frequency applications, behaves considerably better than the silicon carbide, and especially the silicon transistor. So this as a motivation, if you will, why these may be interesting for future applications, but I think I probably didn't tell you anything new about this because we're all in the same field here. Okay, so who of you are familiar with, or who of you are actually crystal growers in the sense that you operate MS3D systems or CVD systems? Okay, a couple, okay, but not too many. So I hope I don't bore. You may look surprised when I tell you things because I'll try to look surprised, but for you this will not be good. So I'll be talking about metal organic chemical vapor phase epitaxy and some basics. Well, first of all, this is quite a little bit 3-5 based, but when we look at the lattice constant and bandgap, this is the eye response curve, by the way. This is where the eye is able to see. Then we can combine group 3 and group 5 compounds. Aluminum, gallium, indium, boron is not so interesting, and nitrogen, phosphorus, arsenic, and antimony. And this is a group 5 anchor diagram, so group 5 is kept constant in this case. You could also come up with, let's say, a group 3 anchor diagram, but this is the one I go with. The aluminum gallium indium phosphide material system covers this. The aluminum gallium indium arsenide covers this. And the antimonides cover this in the infrared. And the nitride system is to the far left of this diagram up here. And I think when you talk about epitaxy, these are the materials, or these are the elements that you can actually combine in order to make your materials. You can think of it in this way. You can essentially exchange gallium for aluminum, and you will more or less stay on the same lattice constant, but you gain a little bit of energy in case of the nitrides quite a lot, but in case of the other materials a bit. And as soon as you add indium, you run off to the lower right of this diagram. And in general, nitrogen, phosphorus, arsenic, and antimony will get you from the upper left to the lower right. And so every time when MOCVD engineers or process engineers put things together, they have to keep these things in mind. It's a bit simpler in silicon carbide, obviously, because that's 50-50% compound of silicon and carbon. So no surprises here. Different epitaxy technologies, MOCVD, MOVP, and OMVP, these are quite interchangeably used. You may come across this one, especially in Europe. This one is mostly used in Asia, and OMVP is how the Americans call it, but it's actually the same and is used interchangeably. At AIXTRON, we are mostly concerned with MOCVD, PECVD, HVP, and AVD, but I'll talk about MOCVD today, so this will be the focus. And I'll go into the requirements and what this means for reactor design. First of all, this is obviously how the circuit designer looks at this thing. This is, I took a light emitting diode here, but the same would be true for a transistor as well. So the device technologies view is like this. You obviously have a lot of layers and contacts and stuff and processing being performed on this. And we start out with this very first process step, which is the MOCVD, which essentially makes a layer cake of material across the entire wafer. And out of that, obviously, the devices are being produced. Now, when you typically draw your diagrams of device structures, you can draw them like this, but this is obviously highly misleading because it more looks like this on a substrate. So in the end, the epi layer that you put on top of the substrate is extremely thin. And when we look at, this is a bit tricky here, okay, here we go. The smallest layers, the thinnest layers, for instance, in a diode or a laser diode, are on the order of 3 nanometers. And if we look at, for instance, the gallium nitride unit cell, we're talking about 5 to 6 unit cells that we need to accurately deposit. And we don't just need to do this, obviously, on a very small scale, but we need to do this on the entirety of the wafer. Because obviously the properties have to be the same everywhere. And I did this little calculation. This is a 200 millimeter wafer. Thinnest layers, as I said, about 3 nanometers, and uniformity requirements are about 1 crystalline cell. And if we want to sugarcoat Belgium, we all need to have still some goals in life. What do you think the requirements would be when you take the same requirement scale on? Any idea?
5 centimeters.
How many?
5 centimeters?
Wow, okay. Anybody lower? Okay. 3 millimeters. And we must nowhere be off by 0.5 millimeters. So this is the uniformity requirement translated from a 200 millimeter wafer to something the size of Belgium. And we need to do this, obviously in production. This is where I said you have to think about cost, and yield is in the end very comparable to cost. We have to do this on every wafer in the reactor. We have to do this during every run and every machine. So also machine system to system needs to be taken care of. And the way we do this obviously is by MOCVD or epitaxis on and ordered, and we have a gas flow with precursors and dopants over a heat substrate, and then this crystal will continue to grow. And by changing the constituents in the gas phase, we are able to change the composition. So everybody knows indium is a green atom, so you can see these nice green atoms in here. and this would be a quantum well of a size of, let's say, 5 to 6 nanometers. And a typical MLCVD reactor consists of a gas blending, the actual reactor, and auxiliary components. And the gas blending usually have a carrier gas, which would be for nitride materials would be essentially hydrogen, except for when you grow indium gallium nitride. This is when you need nitrogen, because hydrogen is a surfactant, which will change the incorporation of the indium into the layer. So you need to be able to change the carrier gas, and you have the group 3 components, trimethyl gallium, trimethyl indium, trimethyl aluminum, and you have obviously group 5 components. Typically a reactor is built for either group 5 with nitrogen, or let's say ammonia, or a classical arsenide phosphide system, because these reactors are fundamentally different in their requirements. So you can't buy one reactor to grow all. You have to actually decide if you want to grow silicon carbide or gallium nitride or something that contains arsenides and phosphides. The reason for this is the heating system. Arsenide phosphides are usually grown at much lower temperatures than nitrides, and the nitrides are grown at lower temperatures than silicon carbide. Then the reaction takes place. Trimethyl gallium plus arsenic, gallium arsenide plus methane, and then you have a scrubbing system to deal with the exhaust gases. Now, the way from the chemical point of view how this works is you have this heated substrate, you have a horizontal gas flow, and you transport, for instance, arsine and trimethyl gallium to the surface. And what's now going to build up is a so-called boundary layer, and this is very important because the boundary layer will actually be a concentration gradient as we move along. So arsine and trimethyl gallium will move into this boundary layer, and for instance, trimethyl gallium will lose a CH3 radical, and what you end up with is a dimethyl gallium. This will move further down to the surface and change to a monomethyl gallium, which is still quite movable on the surface, so it's still able to actually move around and find a nice place to incorporate. And same thing will happen with the arsine, and then the final reaction takes place. And what's important is that if you have a high concentration of trimethyl gallium up here, and you have a 0 concentration of trimethyl gallium down at the surface, because this is essentially where the wafer consumes all the material. And this will cause a diffusion because we have a concentration gradient. And that concentration gradient will hopefully be always totally perpendicular to the gas flow. And that's important, because otherwise this wouldn't work. And that's what we need to consider. Another thing we need to consider is temperature. This is an Arrhenius plot. I adapted this from a quite old paper where someone did this for gallium arsenide. And I put the real temperatures in degrees C up here, and this is the logarithmic of the growth efficiency, which is essentially micrometers per mole. And if we start at the lower temperatures, what we see is a kinetically limited growth, which is essentially governed by the polarization of the species. So if the temperature is too low, that reaction of actually splitting off ligands will not take place. And you have to heat it up more, and then the probability of a ligand splitting off and becomes unlikely. Then we have a stage where it's mass transport limited. So it stays more or less the same. So we can assume that all the species that we put into the reactor actually take place in this chemical reaction. And now it's just a question of how many species I introduce. And then there's another phase, which is C, reduced growth, and this is due to desorption, pre-reactions, etc. So desorption could be that the wafer becomes too hot, so some of the species will evaporate again, so you have a competition between the growth and the evaporation or back etching of the surface. And the second thing is pre-reactions. If the gas phase becomes too hot as well, you will see agglomerations taking place. So essentially, your molecules will already start to decompose well in the gas phase and start to form like little particles that will continue to grow and actually consume raw materials. So this is also not where you want to be. In the end, where you want to be, where you want to operate your CVD reactors here, in this temperature range, because here you are more or less independent of the temperature. The other reason for this is also because you can only control the surface temperature of your wafer to a certain extent, but we will see that as we move along. So what we have to keep in mind is when we are in this regime, we essentially can govern the growth rate of our species by group 3 flow rate. That's the important thing. So if I change the group 3 growth rate or group 3 flow rate of, for instance, trimethyl gallium, I will be able to directly translate this into the amount of, for instance, gallium arsenide growth that takes place. And at the same time, if I now have a similar curve for the aluminum, for instance, I will be able to actually match those and make sure that I get the correct composition of my material. And we'll see when wafers get bigger, these things will become a bit more complicated, but in general, this is how it works. So, production aspects. There is this overarching MOCVD process principle. It's more or less what I just explained to you, and let's now look at different types of reactors. You can separate out the CVD reactors into horizontal flow and vertical flow reactors. Vertical flow reactors are, for instance, showerhead reactors, just like the closed-coupled showerhead systems from AIXTRON. And our competitor has these high-speed rotation reactors, VICO. We took this from a patent. This is actually a picture from a patent, because obviously we, as the competitor, don't necessarily have a nice picture of a VICO reactor, but this is how they look like. So they could also all be characterized as vertical flow reactors. Then we have horizontal flow reactors. Many of you may be familiar with these tube reactors. They were quite well known in research and development in the past, and planetary reactors. And I will talk about the planetary reactors because for, let's say, the wide bandgap materials, they are the material, the reactor of choice for production. The vertical ones are not so interesting, I think, in that context. So, okay, so these are pictures. So this is the planetary reactor. This is a closed-coupled shower and vertical reactor, and I'll talk about this. Let's focus on this one. So how this works is we have an RF coil, not shown here, underneath the susceptor. The susceptor is this rotating thing here. It rotates in this direction, and the RF coil will heat up via an RF heating field, essentially inductively heated susceptor. And then we have the individual wafers placed on rotating discs that we call satellites. So this is the planetary disk, and these are the satellites. And they also rotate, and they rotate on a gas foil. I will talk about this gas foil because it allows us to actually do some tricks with it to improve the uniformity and the yield and cost. And then we have a central gas inlet. It's not shown here. It's actually hangs from the top, and then the gas will flow out radially from the center to the edge where the exhaust is. And then the magic happens here in between. Let's start to understand how a horizontal reactor works. Let's start out with the horizontal tube reactor. So the horizontal tube reactor has an inlet and an outlet, and the wafer is placed in between. It's also rotating here, and it needs to rotate, as we will see. This is a sketch of what we call the depletion curve. So this is the position along the reactor length, and this is the growth rate. And the green curve is the growth rate that we'll see. So we introduce the gases get heated up, they dissociate. Now we're in this point where actually all the gases have their dissociation, so we're in this sweet spot. And now consumption takes place. So all the gases will be drawn towards the surface of the wafer through this gradient, and we'll see a drop in the growth rate towards the outlet. This drop is desired because it actually, when it's zero at the outlet or zero at the end, we have the highest efficiency. We're not wasting anything into the exhaust. So caveat, however, is we need to rotate the wafer in this field in order to have a uniform deposition. So when we rotate the wafer, then this will be averaged out and become a average growth rate, which is somewhere in between with a uniform thickness and composition and so forth. So this is how a horizontal tube reactor works. How do we get to the planetary? So we start out with this. This is the horizontal tube reactor from the top. We have sidewalls, you know, the wafer, the receptor, the inlet, the outlet. And let's now do this thought experiment. We just move the sidewalls out, or in other words, we rotate the reactor around its inlet axis. Just rotate it 360 degrees. And what you end up with is a planetary reactor. So this is how we come from a horizontal tube reactor that we just shown to a horizontal planetary reactor, or something like this. So let's talk a little bit about on-wafer uniformity, wafer-to-wafer uniformity, run-to-run, and maybe system will not touch, and then do some particle avoidance and cassette-to-cassette automation. As I said, we need to talk about cost. Cost is important. The bigger the wafers become, and we're talking now 200 millimeter diameter wafers, because this is the standard. This is what the standard will be. We will see that if we just have a two-level injector, so this is the injector that hangs from the top of the reactor. We have 3 channels for the ammonia, we're still the nitrites here, and 2 for MO. And when I said in the very beginning, it's so easy, you know, you're in that sweet spot and you only have to think about flows and then the rest will come from it and all your composition will be nice and so on and so forth. That's not entirely true if you look at large wafers, because the consumption of aluminum, for instance, towards gallium and vice versa will be different in both cases. So here we have on level 2, trimethyl gallium and trimethyl aluminum. And what we see is the growth rate here. And what happens is that obviously the trimethyl gallium gets decomposed a bit earlier than the trimethyl gallium does. So what this means is that we have a higher trimethyl aluminum growth rate towards the edges of the wafer, whereas the trimethyl gallium comes in at the center. And this means that not just is our uniformity across the wafer not good, but also our composition. Yeah, if we want to have like a certain aluminum gallium composition, then the aluminum content will actually drop at the center compared to the gallium. So we don't want this, and this is why reactors nowadays have to be designed in a way to compensate for these effects. This is done, for instance, in this case, by having this level 4, which is this one, and we can boost, for instance, the trimethyl aluminum with a higher flow at the top. And we can play around with these 2 inlets together with the 3 NH3 inlets in order to account for these effects across larger wafers. And 200 millimeters is not the end. We could do this for larger wafers as well. So this is very important. It's one of the big steps forward to actually make, let's say, MOCVD or CVD for larger wafers viable in the first place. Without something like this wouldn't be possible to do, because then you would only have your sweet spot maybe around the edge of the wafer, and you could throw away the center or vice versa, and you don't want that. So another aspect is temperature control, and I told you that the wafers are actually sitting on a gas foil, so it's actually a spiral, and the rotation gas is inlet here at the center and then lifts up this wafer carrier and puts it into a rotation. And what we also see here is that there's a gap. Obviously, the susceptor is the one which is heated, and the wafer sits on this wafer carrier. And here we have a thermal coupling between the gas foil rotation pocket, if you will, and the wafer carrier. And the flying height is actually the thermal resistance between the two, if you will. So what we can do is, by changing the flow rate, the rotation flow rate, we can change the temperature on the wafer surface. And this is shown here. So we have, we can vary the rotation flow, and we can see that we can get about 25 Kelvin a total span. So we can change the temperature of an individual wafer by up to 25 Kelvin from its ground state. So we can lower it if we're here, for instance. We can lower it by, let's say, 12.5, or we can raise it by 12.5. And this is important to get all the wafers up to the same temperature level, because especially, let's say, for gallium nitride, there's a big influence of the wafer temperature on the incorporation of certain species, especially indium. Indium is very tricky to do, because it's very, very sensitive to the surface temperature. And this is how this works. So we have the susceptor, we have the wafers, they all individually rotate on their GFR, on their gas flow rotation. We have a measurement spot where we do in situ measurement of the temperature. We can do this, for instance, for gallium nitride based applications. Not so easy for the silicon carbide, but for the gallium nitride based applications, we can use a 400 nanometer pyrometer, which is quite tricky to do, because if you look at the curve, the black body radiation curve, and look at 400 nanometers at these temperatures, you are essentially counting individual photons coming from the surface. But with the right equipment, it can be done. So you can actually measure the surface. You're not looking through the wafer, but you can measure the surface temperature of the wafer using such equipment. And as the susceptor rotates, we'll get a temperature profile which is essentially bumps up and down as the rotation takes place. But this can be segmented then into individual temperatures, T1 to Tn, that can be assigned to the wafers. The controller can then change the MFCs, the mass flow controllers, to the gas flow rotation gas channels, and can now lift up or lower the wafers in their pockets accordingly. And this is what comes out. So this is an example. At the outset, when all rotation channels had the same gas, we were about 8 Kelvin in difference. Here at this target temperature around about 920. And once we switched this on, we were able to get all of them together in a band of about 1 Kelvin. And this is where it starts to get interesting, because then the amount of yield that you can produce from such a run is greatly increased. There are some other tricks that I didn't bring here to this conference or to this meeting, which is you can also have a split inner and outer gas foil. You have a gas foil in the center, you have gas foil at the outer edge. And so the number of MFCs and so forth doubles by this, obviously, but now you can actually introduce different gases, like hydrogen. Hydrogen has a much better thermal conductivity than nitrogen does. And like this, we can also change the profile. Yeah? So we can make the edge hotter than the center, or we can make the center hotter than the edge if you want to. And we can overall change the temperature of the pocket. We can do this for every pocket in every wafer. So this is important to get yields up for these devices, because you don't just want your PhD target device that is somewhere at the center of your wafer. You need to do this in a production environment in the end. Another effect, obviously, is particles, and as a simple example, let's have one particle here, and we're producing small devices like small LEDs. Then one device in 1,000 is defective. If we make larger devices, 1 in 100 may be defective, and if we make really large devices, this is especially important for micro LED displays, by the way, because these are, even though they're called micro LEDs, they're extremely huge devices, because you actually have to transfer a whole field from one wafer to the host substrate in the end. So millions of micro LEDs at the same time. And just one of them is broken, then your display is broken. So particles are very important. Under normal circumstances, you work around the particles, but there are many cases where you can't do this. So you have to avoid them at all costs. So yield depends on device size, and also power transistors are quite large devices, so plays into that as well. This is an example of a reactor, how it looks like after 4 micron of a hand run. Mostly aluminum nitride is quite difficult to get rid of. And what you see is, this is the upper side of the injector, this is the lower, and you can see deposition everywhere and parasitic deposition. And if this builds up, this will automatically lead to particles because they get blown away by the gas and so forth. And so you want to avoid this. And using certain proprietary, if you will, etching techniques. This is the same reactor one run later after the etching has been performed. So what I want to actually tell you with this is that reactors can be reset in situ. So you don't necessarily have to open it or replace things and scrub the ceilings and scrub all these parts. You can do this in situ without operator intervention. And operator intervention is something we want to avoid because we want to go to automation. So fabs, especially we heard about the ISO 1 fab where there is no human interference allowed. We're not, I think we're not that far yet in compound, but we have to get there, which means that there is no way that an operator will open the reactor in between runs and take out the wafers and put in new wafers and scrub reactor parts and so forth. So what we need to have is automation where we have cassette to cassette. And this is an example of 2 MOCVD systems and a cassette to cassette handling unit in between, which then allows to load and unload wafers into both reactors. Important here also, MOCVD runs, for instance, for gallium nitride transistors are extremely long. They can take up to 7-8 hours depending on the type of device that you want to grow. Which means that just having a handling unit attached to one of these reactors and then letting this sit still idle for 8 hours until the action comes is a bit waste of money. So actually what you need to have is several of these reactors hooked up to the same handling unit. That makes the whole thing a lot cheaper. And this is why this is an example of 2 reactors. You could in theory also attach a third one towards the back in this particular design. So this is nitrides. This is a quite newly introduced reactor for silicon carbide, G10 series. All I've shown so far is G5, but this is G10. Things like trichlorosilane refill automatically. Don't need to change bubblers and stuff. You have cassette to cassette handling. In this case, with open cassettes, where you can grab up to 2 cassettes in order to run this reactor. And size matters in gallium nitride as well as silicon carbide. Typically 150 millimeter diameter. This is silicon carbide. 9 times 150 and 6 times 200. I will show some growth results on 200 millimeter silicon carbide compared to 150 millimeter silicon carbide later on. As well as gallium nitride also moving to 200 millimeters because the silicon wafers are readily available. And so 200 millimeter silicon is the mainstay currently, at least moving into this direction. There may still be some people using 150 millimeter at this time. Okay, here we go. So let's first talk about gallium nitride and silicon heteroepitaxy. Let's see what the time is. Okay, still 45 minutes, right? Okay. So gallium nitride, silicon heteroepitaxy for horizontal power transistors. This is a bit like the genealogy of power transistors in the nitride field. So before 2013, this is what the stack looked like. So we have we have a nitridation at the surface between the silicon and the 3,5 material. That became a little bit more complicated because carbon-doped gallium nitride buffers were introduced. I think Farid talked about this to some extent this morning. So this was around about 2013 to 2015, and important here is that we still have staircase buffers. Then 2015 to 2018, we changed to metallization, which in the end is the difference in the way that we start the growth, nucleated growth down here. And nowadays, what we grow is super lattices. So to dissect this, this is the actual transistor structure. So this is the payload of the entire structure. This is what we want. And all the rest is extra stuff that we need to do to make it work. Then we have the 3,5 on 4 epitaxy, very tricky because 3,5 and 4 don't necessarily match very well. And next thing is the carbon-doped buffer to basically insulate the transistor structure from all that we're doing down here. Then we have the staircase buffer, and nowadays we have the superlattice, which can be up to 150 pairs. And this is actually what takes up most of the time of the growth, to be honest. And all of this you need to do in order to make the transistor work. So let's see. So what's the magic sauce? What we want in the gallium nitride silicon power amp, we want high breakdown voltage, of course, we want low leakage current, decent performance, static and dynamic. And desorption predose. This is when we start growth on the silicon surface. So we need atomically smooth surfaces, excellent crystal quality, obviously, because everything here has an impact on the electrical behavior of the transistor. Initial aluminum nitride growth, as I said, predose or things like that, inversion channel formation that can happen down there, not desired. Alternative technology, super lattices, this is the mainstay now. Enhancement mode, aluminum gallium nitride back barrier. I think already talked about this. We're not doing this at this stage because we feel that currently our transistors work the way we expect them to. And so there's been no need at this point. We tried it in the past, but we've given it up again. Environment, that's particle and automation, plays into this. Carbon doping of the gallium nitride carbon dope buffer, we need decent buffer performance, obviously. External doping is possible using hexene or auto-doping. Auto-doping, why auto-doping? Because when you look at the group 3 precursors, there's a lot of carbon in there. So you have a lot of carbon floating around the reactor anyway. And that can be used in order to incorporate this into a use as a doping facility, then you don't need extra carbon. In situ cleaning, this plays hand in hand with automation, reliable and reproducible it needs to be. Chamber conditioning, do we need to pre-coat the chamber? I think sometimes we do, because a clean chamber does not necessarily always work. And sometimes you want silicon nitride capability as well. And all of this needs to play into this. I think I talked about this more or less, so let's focus on some other stuff. This is an example of the interface between aluminum nitride and silicon. So usually you can have sharp areas and disordered areas in there, and then it bonds obviously because silicon is group 4 and aluminum nitride is 3,5 semiconductors. So you have damaging bonds. They are unavoidable, but they also help reducing the strain in this area. However, obviously, they can give rise to certain effects that lead to a channel that can lead to breakdown. Another effect, obviously, is we want this. The silicon is a dopant, obviously, in 3,5, so we don't necessarily want the silicon to go deep into our 3,5 layers. So we want this interface to be as abrupt as can be. Here we see that it's a couple of atomic layers until the silicon, which I think is the red one, the red curve drops down, so we still have some cross-doping in this case from diffusion, probably in diffusion of silicon into the aluminum nitride. Another effect that's important to look at is slip lines. Silicon is very susceptible to this. So the slip line can happen when the shear forces become too large for the silicon crystal to handle. So what it does is basically it slides a couple of planes. And this is an example of a slip line. And I put this picture that I drew here in here to show you the slip line. I think I'm not sure if you can see it well, but it's a darkened area here. And this happens when you have when you're above the strain threshold. Silicon wafers are they have a certain stiffness towards these slip lines, and this can be modulated by doping. So typically, boron doped, for instance, or oxygen background that may be in the wafer that can modulate this. So high doping, however, introduces defects. So what we found is that 2 to 4 milliohm centimeter currently shows the best performance for these wafers because that's when they are the stiffest. The thing is, slip lines can occur when you heat up very quickly. This is the general problem that the semiconductor industry has. But also, remember, we are growing strain material here. So we have quite high amounts of strain depending on the process step. And this will or can introduce slip lines and they need to be avoided. And this is an example of curvature. And curvature in the end will result in strain. It's from one run, this is 5 by 200 millimeters. So here we have the satellite 1, so this is actually 7 runs copied into the same picture. And we measured the curvature using a laser curvature measurement tool, which actually projects 3 spots onto the surface. And the reflected laser spots will then be read out by a CCD camera. And from the relative positions of those spots on the reflection, you can actually determine the curvature in 2 dimensions. Right, because you have like a triangle of spots that you project on the surface. And this is the result. If the curvature is positive, you are concave. If the curvature is negative, you're convex. And what you see here is the curvature development over the entirety of the run. And we see that this can really change greatly. So you are concave and then you grow. I think this will be the buffer. You suddenly become very negative, convex, until you get a bit more positive again. And in the end, what must happen is that this must not exceed a certain value, because otherwise you introduce these slip lines. And at the same time, you want to be more or less at 0 at the end of the run, because otherwise your wafer will not be able to be processed. Because if it's too warped, you will not get good lithography. At the same time, this is also an interesting measurement, and here we are again yield territory, when we compare the different wafers, because an outlier, a bad wafer, a bad egg, will directly show, because it will completely go astray and have completely different properties. So from that point of view, the curvature measurement is also a very good tool to sort of assess how well your run is performed and how your wafers have performed in this run. And this is an example of the average of all the wafers for the different runs. It's essentially not just taking wafer number 1, but it's taking all the wafers. And obviously you can see that they're more on top of each other in this case. So 7 runs repeated, you can actually be quite uniform or quite reproducible. This again, talking to reproducibility here from run to run. And taking curvature as a measure. This is the same set of runs, but this time looking at thickness. So we're looking at the thickness distribution. Wafer 1, 2, 3, 4, 5. 5 wafers, 200 millimeters diameter. And you can see that the thickness distribution is about 37 nanometers. So we're at about 1% thickness distribution. This will become interesting when we look at the threshold voltages of transistors later on. And this is a composition measurement. It's still from the times of staircases. So you can see the staircase buffer, you can see the gallium nitride, the aluminum nitride, and then the staircase all the way down to the gallium. How many runs are those? 6, 7, 8 runs, 7 runs. And you can see that they're essentially all on top of each other in the 6RD curve. So what you can see in this is that we're also able to quite very nicely reproduce the amount of aluminum that we put in, so the aluminum-gallium ratio for these layers at different concentrations. And this is what happens when you do everything right. So this is a TM image of the approximate position of the 2D EG. And you can see that this looks quite nice, lower resolution, a higher resolution. So this is what the payload actually looks like all the way micrometers up from the interface between the silicon and the 3-5. Okay, some electrical measurements. They are done in collaboration with, this is actually not done by us, but I'm reading into this, but all of the electrical measurements that I show are done in collaboration with IMEC. We at AIXTRON, we do not have capability to process devices, so we send them out to IMEC, and IMEC make the devices and do the characterization for us and send the data back to us. But this is not from us, but this is from a paper that looks into the effectiveness of the carbon doping in gallium nitride buffers. We're looking at this buffer here, and it looks at the breakdown, if you will, breakdown being defined as a current of 10 microamps per square millimeter when you increase the doping. And what you see here is that the saturation of the blocking voltage is around 10 to the 19 per cubic centimeter. So this is essentially, up to that point, you can do some carbon doping, but above that does not actually give you any more blocking voltage for that. So this is why I think it would make sense to actually stay below that. And this is an example of such a layer that was grown by us. So this is the SIMS detection level, and what's important here is obviously that you don't carry all the carbon into the active layers, because otherwise you would be doping the active layers, which you don't want. So here the doping was almost up to 10 to the 20, and then the doping was switched off, and we were able to actually go down to the detection level. And this is a prerequisite in order to grow your transistor, because you have to come down from quite high carbon concentrations down to almost zero, so that nothing actually interferes with your actual device structure. So oxygen, silicon anyway, but also the carbon goes down to into the detection limit. And when you do this, we can do some nice measurements. So for instance, buffer dispersion measurements. So we stress, essentially this is a TLM structure that has a back contact back on the silicon substrate, and the stress voltage of minus 650 volts is applied between this ohmic contact and the ohmic contact down here for 10 seconds, and then you wait. You wait either for 10 milliseconds up to 10 seconds, and then do a TLM measurement. So essentially measure the resistance between those two contacts. And we did this at room temperature and 150 degrees C. And what we can see here is this. So essentially rest time is a function of rest time, goes up to maybe 10 seconds or so. And this is the resistance between those two contacts after this rest time. For 25 room temperature, if you will, and 150 degrees. So what we can see is this is the 95 superlattice buffer and this carbon doped interlayer. And what we see here is that there's actually no dispersion. The resistance that comes out is actually more or less the same, depending on break time. So this gives us confidence that this carbon layer works. This is a gate injection transistor design. I think I'm not the super duper device expert, so I'm not going to talk about this very much, other than this is, I think, also the University of Ghent, right? It's a simulation of the aluminum-gallium barrier mole fraction and the aluminum-gallium barrier thickness, and its effect on the threshold voltage. It's a simulation. And if you look at this, you actually, I think the device specs are that the voltage, the threshold voltage must be, delta in the threshold voltage must be below 0.3 volts across the wafer, otherwise you're actually out of spec. So this corresponds to 0.8 nanometers thickness variation, 0.8 nanometers thickness variation, and 0.7% aluminum concentration variation if you move around in this plot. And this brings us back to the thickness measurements and the aluminum concentration measurements that I've just shown you, which basically are a prerequisite in order to achieve these specs. Because if you're floating around with your aluminum concentration or your thickness all over the place, then you will never be able to achieve this. And remember, this is again my favorite 1 unit cell in gallium nitride. And what we've done is we've actually measured the threshold voltage of such transistors, again, from the collaboration with IMEC, using this buffer stack and the transistor structure on top. And UDS was kept constant 0.1 volt, and UGS was set between -2 and 7 volts. And the threshold voltage was defined as the voltage where the IDS actually becomes 10 microamps per millimeter. So that was our definition. And this is the result for all the transistors made on one 200 millimeter wafer. And oops, the 10 microamps per millimeter is here. And the threshold voltage is down here. And this will be then the delta threshold voltage. And the actual results I can show here. So it's a wafer that has between 1.3 and 1.4 volts threshold voltage all over the place. So even at the wafer edge, there are no outliers. And this is where you need to get to such kinds of uniformities. Otherwise, you not be able to actually make a product. And you have to do this across 200 millimeters. Just a few words on vertical power transistors, gallium nitride and gallium nitride homo epitaxy. I think touched on this before. This is the structure. It's a different project. It's a German national project in this case, YESvGaN, which addresses this, and this is a project that actually intends to make a vertical gallium nitride transistor that can handle 1,700 volts. So this is the target. So the actual transistor, as you know, is here, and then we have an undoped layer, which is grown by MOCVD, and we have an N+ substrate, which is the gallium nitride substrate that we need to use for this. Prohibitive was the word I think that he used in order to characterize gallium nitride substrates at this point, especially compared to silicon. Yes, absolutely, no question. But I think there are a lot of people working on gallium nitride substrates at this point. I've seen some nice work coming out of Japan recently, where they're going for 4-inch, even larger gallium nitride substrates. Cost still will be a factor, but I think we are looking, let's say, maybe 10 years ahead or 15 years ahead. The cost may also come down to some extent. So what we've done is, this is a 200 millimeter wafer pocket. Unfortunately, the wafers are just 2-inch, not too big. This is HDPE grown material from Freiberger, and then we had to actually cut up a couple of a couple of sapphire wafers and make nice masks in order to fit the wafer in there. So this looks like it's a little bit playground for our PhD students as well that we have, and and then. The rest is just parasitic growth on 200 millimeter sapphire wafers or silicon wafers that we just put in. The layer that was grown was 2 micron N+ drift layer on top of the highly doped gallium nitride wafer, and then 5 micron low doped gallium nitride. There's a cap layer on top as well. Yeah, it's magnesium doped, I think. And we have to relearn how we do epitaxy, because all the things that we know about heating up and nucleating and so forth are completely different. But this shows that it works actually. And the interesting thing about this is, and this was quite astonishing, we even get a reflectance signal out of it, which is kind of unusual because we're doing normal epitaxy, so there shouldn't actually be an index jump between the substrate and the layer. But we probably attribute this to a difference in doping. And by the way, this is, I think, a factor 100 or 1000 where the reflectance is blown up. But for comparison, the green one is the gallium nitride with silicon. You can see that actually the growth rate is the same, and this oscillation is indeed coming from the layer that is grown. So this is very early results. I can't show much more of this, but just to show you that we're working on this as well, and it's interesting to see what's coming out of it. One point will be to correlate wafer defects that were characterized before growth, because wafers are characterized before growth. I think Elke has a talk tomorrow from ISB. She's in the project as well. I don't think that she'll talk about this, but maybe she does. So we're characterizing the defects prior to growth and after growth to see what defects in the original gallium nitride wafer were actually penetrating through, and how this actually corresponds to the device performance that is done later on. Okay, now silicon carbide growth considerations and results. Well, all I said about automation and all the uniformity things that I talked about are applicable here as well, even though this is not MOCVD, this is CVD, but it plays into the same concept. The process is a lot easier, because this is temperature profile just showing how this works. This is you just heat up, then you do some etching. This etching will be very important, as we see, to actually deal with the basal plane dislocations that we just heard about from ST. And then we do a buffer, and then we do the drift layer and we cool down. So essentially, this is a quite easy process compared to gallium nitride based processes where you change the temperature a lot. So you're all over the place between 700 degrees and 1050, 1150, and you cool down into 800 and so forth in order to grow different layers. So this is not necessary here. One thing about the growth of silicon carbide, well, first of all, it's step flow growth, just like with many of the semiconductors that are grown in CVD or MOCVD. So we have a terrace, and we have this step, and we want the atoms to actually migrate all the way to the step and then continue the growth in this direction. So the growing crystal actually takes what it sees here at this edge as a template to continue growth. This is why the terraces, for instance, should not be too big, because if they are too big, then I'm an atom, I come along, I linger around, I think, oh, this is a nice place, I'll just settle down here. And then I start growing an island. And this island will not actually take over the same less parameters as I want to have. I want to have for H. But as we know, 3C is always around the corner, and 3C actually spoils our device. So, we want a certain off-cut angle, tilt angle. We don't want this angle to be too flat, because then the terraces become too large. We don't want it to be too steep, because then I don't get a diameter out of my hole, because I have to cut a certain angle. So this is for the device, for the wafer growers, more of the aspect. So 4 degrees, by the way, is what we use. And these are the polytypes, and 4H is the one we want. 3C is the one that unfortunately wants to grow all the time in non-equilibrium conditions, such as CVD, especially at the growth temperatures that we're looking at in CVD, which are around 1600 degrees. So any disturbance to my 4H growth will automatically result in a 3C crystal, or 3C inclusions, or 3C defects. So, for instance, effects of particles, micropipes, dislocations. For instance, I have a particle or something, some growth defect here at the site on the edge of my growth front. Then the crystal, the growing crystal, will not know what to do because I'm disturbing it, because it wants to grow along this edge. And what's going to happen is that, for instance, this converts to 3C. And this gives rise to these triangle dislocations or triangle defects that we see. So any disturbance of step flow growth leads to the 3C polytype. Another thing that we just heard about is basal plane dislocations, BPD. I think the talk by ST was touching on this. So the basal plane dislocation will continue to grow into the EPI layer, and this is a photoluminescence, UV photoluminescence micrograph that shows these dislocations. This is when they're coming out of the substrate and move into the EPI layer. They're usually not visible, so this is the photoluminescence, so basically a picture, if you will. So you have UV light shining on the wafer, and then they will light up at certain wavelengths. I think around about the green or orange. Well, I'm not sure, because this is black and white, obviously. So they're invisible as long as they are in the substrate, because the substrate is usually highly doped, and this doping shields any photoluminescence effects. But once we grow like a low doped silicon carbide on top of it, these basal plane dislocations will show up. And on this micrograph, this is about 500 microns. So this is not like very small. This will be a very small part, is 0.5 millimeter that gets destroyed on the surface. So we don't want those. What we can do is, during the start of the growth, we can try to change them into threading dislocations. And they then move up and penetrate the surface. I'm not sure, this picture doesn't tell me much, but the device technologist tell me that this is showing exactly that effect. I leave it to interpretation, but what in the end I want to tell you about this is that these basal plane dislocations, they lead to a recrystallization of material to the 3C polytype in the vicinity when you make your device. So, and this can actually, and that's 3C has about 1 eV lower band gap than the 4H, which means that your device will be shorted up after a couple of hours. So I think its fields is combined with elevated temperatures during operation. And then this will change, the basal plane will change into like 3C, and in the end, it short circuits your device. And this is one of the main causes for device failure, and it's undetectable during device fabrication and testing. So this will only happen when the device is in operation, when it's at the customer, and the customer calls you up and shouts into your ear that the devices have failed. So it's important to reduce them, and it's important to detect them. I don't know how to detect them, but how to reduce them, we've worked on. And this is an example. It's 150 millimeter diameter wafers. It's from one run, so all 9 wafers from that one run. And they were counted, so on the order, the typical substrates that we used have about 500 BPD per square centimeter. So that's when they come out of the box. So that adds up to about 100,000 per wafer. So basically, no device would ever work because they will all be short-circuited at some stage. But we're able to actually get them down to single-digit numbers, and this is something you can work with. So from 100,000 down to, I think, 7 here was the highest count from this run. Is quite an achievement. It actually gets you into a realm where you can actually make devices on a large scale. And this is to do with this extra buffer layer that we use in the desorption edge step. Another important thing is thickness uniformity. Again, this may not be as important as sometimes in the 3.5 compounds, but still. So this is an example from a from 150 millimeters, so that's 9 by 150 millimeters, and you can see that there's about 3 point something percent at 8 microns thickness for all the wafers. And what you do on 150, you also need to do on 200 millimeters. So this is 200 millimeter configuration, 200 millimeter silicon carbide wafers, and also, unfortunately, someone in our lab was wise enough to actually measure one in sigma and the other one in delta. I don't know why, but anyway, you can see that when you just look at these diagrams that we're in the same ballpark, which means that scaling up from 150 to 200 millimeter diameter wafers is feasible. And this is the same result for doping. So this is a doping profile across the same 9 wafers, 150 millimeters. So we're at 3.4% doping, and a similar result here for the 200 millimeter wafers as well. So doping and thickness uniformity can be achieved for silicon carbide as well using CVD technologies. Yeah, this is reproducibility. It's also the I think this is it's also 200 millimeter wafers. We've done 30 wafers split over 5 runs, and you can see the thickness quite uniform, reproducible from wafer to wafer, from run to run, as well as the doping stability. So we will say that this is setting the stage actually for commercialization of 200 millimeter silicon carbide products when they become available or when they become interesting for the industry. And that's it.